I want you to close your eyes for a second. Imagine you're the plant manager of a massive pharmaceutical factory.
Okay.
You are not making widgets or toaster ovens. You are making life-saving medicine. Maybe it's a cancer treatment, a vaccine, heart medication. The pressure is just
It's
immense.
an incredibly high-stakes environment. I mean, there is zero margin for error.
Exactly. And here's the reality of your day-to-day in a traditional setup. You finish making a batch of this critical drug. It's done. It's sitting there in a sterile container.
But you can't ship it.
You cannot ship it. You cannot get it to the patient. For 10 days, it just sits there.
That's the industry average, which is just wild. 10 days of paperwork, quality checks, manual reviews, all after the product is physically ready.
It's trapped in this, bureaucratic limbo. Now, what if you could cut that time by 40%?
Right.
What if you knew a critical pump was going to fail 3 days before it actually stopped working? That is the promise of the topic we are unpacking today, Pharma 4.0.
And looking at the stack of research we have, especially this implementation playbook, it's so clear this is no longer just a buzzword. It's not a promise.
No.
It's happening now. The data shows companies deploying these smart manufacturing technologies. They're seeing equipment uptime improve by 20 to 30%.
And like you said, they're cutting those batch release cycles, that limbo period, by 40%.
Which means getting drugs to patients days faster.
In this industry, that isn't just efficiency. That saves lives.
It does, but we have to be realistic about the lift required here. This isn't about buying a few iPads for the factory floor or slapping some Wi-Fi sensors on a tank.
No.
This is a fundamental transformation of the 3 pillars: your people, your processes, and your technology.
According to the technical report we're looking at, we are at a really serious inflection point.
We are. The source highlights this massive divide forming in the industry. You have the first movers, the giants, Pfizer, GSK, J&J, who are already seeing these gains.
And then you have everyone else.
Then you have this staggering statistic. 64% of companies are still in the early stages or haven't even started.
That is a dangerous place to be. If
Yeah.
you're in the 64%, you are not just treading water. The gap is widening every single day.
You're becoming obsolete. Precisely.
Mm.
So our mission today is to try and bridge that gap. We're going to unpack the 24-month roadmap provided in this playbook.
Okay.
We need to dissect the 5-layer stack, and maybe most importantly, we need to answer why some pilots succeed and others just crash and burn.
Let's start at the bottom then, the foundation. The report talks about a 5-layer smart manufacturing stack. It sounds super technical, but they describe it as the nervous system of the factory.
That's a great analogy. It really is. Layers 1 and 2 are your physical equipment and your sensors. Think of these as the eyes, the ears, the fingertips of the whole operation.
So this is the IoT, the Internet of Things. But what are we actually measuring here? What kind of sensors are we talking about?
We're talking temperature, pressure, vibration, motor current. I mean, in a traditional factory, an operator might walk by with a clipboard and check a gauge, once an hour?
If that.
If that. In a Pharma 4.0 factory, these smart sensors are streaming data every millisecond.
It's the difference between taking one snapshot a day and watching a live 4K video stream.
Exactly. And the report makes a really critical point about scale. A lot of companies, they'll start with a pilot project. Maybe 100 sensors on one line.
Which seems manageable.
It is, but the goal is enterprise rollout. We're talking 500 to 2,000 sensors per site. And that brings up the unique headache of the pharma industry.
Validation.
The dreaded V word, validation. If you're making cars and you want to stick a vibration sensor on a robot arm, you just do it.
Right.
In pharma, because of GAMP5 standards, you have to validate absolutely everything.
Okay, so for listeners who aren't living in the compliance weeds, what does that actually mean? Break down GAMP5 for us.
It means you have to prove with a mountain of documentation that the sensor works, that it's accurate, that it's secure, that it can't be tampered with, and that it's going to perform reliably over time.
And you multiply that by 2,000 sensors.
That is a mountain of paperwork. It's not just a technical challenge, it's a huge bureaucratic one.
Wow. Okay. So once you get that data flowing, you hit layer 3. And this is where I think I had my biggest aha moment reading the source.
You're talking about the critical missing link.
The disconnect between the MES and the ERP.
Yes.
Let's decode that acronym soup for a second. MES is?
Manufacturing Execution System. It's the shop floor software where the drugs are actually made.
And ERP is the business software.
Enterprise Resource Planning.
Yeah.
Exactly. Sales, inventory, finance. The problem is, in most factories, these two systems speak different languages. They live in different time zones.
And the report has this great example, the 2 p.m. versus 8 a.m. problem.
I loved this too because it is so frustratingly real. So imagine you're an operator. It's Tuesday, 2 o'clock in the afternoon. You finish a massive batch. You type into the MES batch complete.
So the factory knows it's done.
The factory knows, but the business side of the house has no idea
Why?
because there's no real-time link. That information just sits in the MES until a scheduled data dump, which usually happens at like 8 a.m. the next morning.
So for 18 hours, the ERP system, the one that sales is looking at, thinks you have zero inventory.
Exactly. A sales rep could be looking at their screen at 4 p.m., seeing a hospital that desperately needs this drug, and the system says, out of stock.
Meanwhile, the product is literally sitting on the loading dock.
It's a ghost inventory. It's incredibly inefficient. The fix, according to the playbook, is APIs.
Application programming interfaces, basically a digital bridge.
A digital bridge. Instead of a once-a-day data dump, the systems are constantly talking. The operator hits complete at 2.0 p.m. The ERP updates at 2.05 p.m.
You go from an 18-hour blind spot to 5 minutes of visibility.
And that creates what they call available to promise inventory accuracy. You know exactly what you have, and you know exactly when you can promise it.
And just to wrap up the stack, layer 5 is the cloud.
Right. And the emphasis here is just sheer volume. The report talks about data lakes. You need a system that can handle ingesting maybe 500 gigabytes of data a month, or even more.
You can't run this on a local server in the basement anymore.
Not a chance.
Okay, so we have the nervous system, we have the sensors, the data flow, the cloud storage. Now let's talk about the brain, layer 4. Analytics, AI, and digital twins.
This is where it gets really interesting. We move from just collecting data to doing something intelligent with it. And the first big application here is predictive maintenance.
I think most people get maintenance, you fix things, but the source breaks it down into 3 stages: reactive, preventative, and predictive.
Right. So think of it like owning a car. Reactive maintenance is you drive until smoke pours out of the hood and the engine seizes up.
Which, in pharma, is a complete disaster.
It's a catastrophe. If a machine breaks mid-batch, you can't just hit pause. The biological material might degrade. You often have to just dump the entire batch.
Millions of dollars down the drain.
Potentially. So then you have preventive maintenance.
Changing your oil every 3,000 miles.
Exactly. Whether you need to or not, it's safe, but it's wasteful. You might replace a perfectly good pump seal just because the calendar says so.
And that leaves predictive as the sweet spot.
Predictive is your check engine light, but on steroids. It uses machine learning algorithms, things like LSTM or random forest models, to analyze all that vibration and temperature data we talked about.
It's looking for subtle patterns that a human could never spot.
Never. And the accuracy stats in the report they're just wild.
They really are.
These algorithms can predict an equipment failure 72 hours in advance with 85 to 95% accuracy.
72 hours. I mean, that changes everything.
It does. You get an alert on Tuesday that a bearing is going to seize on Friday. You don't panic. You just schedule the repair during a shift change on Wednesday. You save the machine, and more importantly, you save the batch.
And the ROI on that must be immediate.
Oh, yeah. Depending on the drug, avoiding one single downtime event can save anywhere from $500,000 to $5 million.
It pays for the entire sensor rollout in one afternoon.
Pretty much.
But the real star of the show in this section, the concept that feels the most futuristic, is the digital twin.
Oh, absolutely. This is the game changer.
So for anyone listening who thinks this sounds like something out of science fiction, what is a digital twin in this context?
A digital twin is a high-fidelity virtual replica of a physical system. So imagine a perfect computer model of your bioreactor or your filling line. It's not just a 3D drawing. It understands the physics, the fluid dynamics, the thermodynamics. It behaves exactly like the real thing.
So it's a hyper-realistic simulator.
Exactly. And the applications are incredible. First off, virtual experiments.
And the report compared the costs here, something like $5,000 versus $100.
Right. So let's say you want to see what happens if you increase the mixing speed by 10%. In the physical world, that experiment costs $5,000 to $50,000. You have to clean the tank, prep the materials, run it, test it.
You might break something.
Or ruin the product. But on the twin, you just run a simulation in the cloud. It costs maybe $100 in compute power. You can run 1,000 crazy experiments and it costs you practically nothing.
Which leads to the second application that I found fascinating, tech transfer. This is a huge bottleneck, isn't it?
It's massive. So A small biotech firm invents a new drug. They figure out the recipe in their little lab. Now they need to hand that recipe off to a big contract manufacturer, CDMO, to make it at scale.
It's like giving your grandma's cookie recipe to a giant industrial bakery.
Perfect analogy. The equipment is different, the oven is different, and that tech transfer process usually takes 12 to 18 months. It's just endless trial and error.
So with the digital twin,
You simulate the transfer before you ever move a drop of liquid. You take the digital twin of the contract manufacturer's equipment, you load in your recipe, and the computer tells you, hey, that mixing speed won't work on this tank size, you need to change it to X.
and the source says this cuts the timeline from over a year down to just 3 or 4 months.
Think about that. That is getting a drug to market almost a year faster. I mean, that's huge for the business, but it's even bigger for the patient who's waiting.
And then for the daily grind, you have this concept of the golden batch.
I love that name, the golden batch.
Explain it.
It's based on historical data. You take all the data from the best, most perfect batch you ever made, the one with the highest yield, the purest product, and that becomes your golden batch profile.
Like a benchmark.
Exactly.
Right.
Then the digital twin monitors your live production run and compares it to that perfect profile in real time.
It reminds me of those racing video games where you race against a ghost car of your best lap.
That is the perfect analogy. You're racing against your own best performance. If the live batch starts to drift, say the temperature trends up just 1 degree, the system sees you're falling behind the ghost car.
Even if you're still technically within the safety limits.
All right, it catches the drift days before it becomes an actual failure. It nudges the operator, hey, correct this now, or you're going to lose the race.
Okay, so the tech is incredible. But implementation is where dreams go to die. You can't just flip a switch on Monday morning and have all this stuff working.
No, absolutely not. The source is very emphatic about this. It is not a big bang rollout. If you try to change everything at once, you will fail. It is a disciplined, 4-phase, 24-month roadmap.
Let's walk through that timeline. Phase 1, months 0 to 3, assessment and pilot. What's the key to not messing this up from the start?
The most crucial decision is picking the right pilot. And this is where, honestly, politics often kills the project before it starts. People get scared. They don't want to mess with the cash cow production line, so they'll say, oh, let's try this smart sensor stuff on that old machine in the corner we barely use. If it breaks, who cares?
But the report says that's a trap.
It is a fatal mistake.
Yeah.
If you pick a machine nobody cares about, then nobody will care about the results. You won't prove any business value. The source says you have to pick a high ROI asset.
You have to be brave.
You have to be brave and put this on a commercial bioreactor or a critical filling line. You need a quick win, something in 6 to 12 weeks, that makes the CFO look up from their spreadsheet.
Okay, phase 2, months 4 to 8, expansion and validation.
Now you scale. 2 or 3 lines. You integrate the digital twin. The metric you're watching here is batch release time. You need to see that number drop from 10 days to 7. You have to prove the efficiency.
Then phase 3, months 9 to 18, enterprise deployment.
This is the heavy lifting. Now you're rolling it out to all sites globally. The focus shifts to things like changeover times. Can you reduce those by 15 to 20%? This is where the real economies of scale kick in.
And finally, phase 4, months 19 to 24 and beyond. Optimization. This is where we get into that sci-fi stuff again. Autonomous control,
This is the ultimate goal. The loop closes.
meaning the AI recommends a change and then it just does it.
It just does it. The human operator doesn't even have to press the button. The system sees the temperature drifting, it calculates the fix, and it adjusts the cooling valve automatically.
And this leads to something called real-time release testing, or RTRT.
Which brings us full circle. If the process is monitored and controlled so perfectly by the AI, you don't need to hold the batch for 10 days of testing at the end. You know it's good, you release it immediately.
Now, we've painted a very rosy picture here, but the report has a huge section on pitfalls and the human element, because the tech is only one pillar.
Yeah.
So why do these projects fail?
The first big pitfall is the data integration strategy. It's the mistake of assuming data will just integrate automatically.
Which it never does?
Never. The report points out the chaos of legacy data. You might have 50 sites. At one site, your product is listed as aspirin 500 milligrams. At another, it's AST 500.
A human knows that's the same thing.
That a computer sees 2 completely different products, so if you just dump all that into a data lake, you don't get a lake, you get a swamp.
You have to clean the house before you invite guests over.
Exactly. You need master data governance. You have to define the dictionary before you try to write the book.
Pitfall number 2 was about validation again. They call it the waterfall trap.
This is that old school mindset. You build the whole system, install all the sensors, write all the code, and then at the very end, you try to validate it.
And if you find a problem then,
You are in big, big trouble. It's like building a house and waiting until the drywall is up to check if the plumbing works. If there's a leak, you're tearing the whole thing down. It creates 12-month delays.
so the solution is,
Risk-based Game 5. You validate as you go. You check the plumbing while the walls are still open.
okay, Pitfall 3 is my favorite because it's purely psychological. Change management.
Mhm.
And the report really takes aim at the train-the-trainer model.
Oh, yeah, we've all seen this. You send one expert to a training seminar. They come back and train a manager who trains a supervisor who then trains the operator.
It's the game of telephone.
It is. By the time the message gets to the person who actually needs it, the knowledge is diluted or just plain wrong, and the operator feels totally disconnected.
So what's the fix?
The Operator Champion program. You identify the real influencers on the floor, that 20 or 30% of staff that everyone else looks up to. You invest heavily in them. You make them the experts.
And you have to show them the benefit. You can't just say, do this because corporate said so.
You have to answer the what's in it for me question. If you tell an operator, look, this new dashboard means you don't have to spend 2 hours a day handwriting numbers into a logbook, they will love you for it.
So you frame it as, this robot isn't here to replace you. It's here to do the boring paperwork you hate so you can actually do your real job.
Precisely. If you win the hearts and minds of the operators, the tech will work. If you don't, the most expensive sensors in the world will not save you.
And finally, pitfall number 4, security.
This is the one that keeps CIOs up at night. The second you connect your factory to the internet to get all this amazing data, you're opening a door.
And there are horror stories.
The report mentions ransomware attacks on IoT-connected systems causing 48-hour production halts. I mean, that's a nightmare.
So the requirement has to be strict.
It has to be. Network segmentation. The manufacturing Wi-Fi has to be totally air-gapped from the business Wi-Fi where people are checking email and clicking on shady links. And you need TLS 1.3 encryption on everything.
Security cannot be an afterthought.
It has to be baked in from day one. Never.
So bringing this all together,
Yeah.
the ROI seems pretty clear.
It is. The payback is usually achieved in 18 to 24 months. You're looking at annual savings of $1 to $3 million per site.
And the big players are already there.
The window for being an early adopter is closing fast. If you're not moving on this now, you are playing catch-up.
I want to leave our listener with a final thought, and it comes from that Phase 4 idea of autonomous control.
It's a fascinating and maybe slightly scary concept.
Right. If the factory of the future effectively runs on autopilot, if the algorithms are tweaking the temperature, predicting failures, and releasing the batches, what does that mean for the role of the human being in the factory?
That is the big question, isn't it?
Are we moving from a world of making drugs to a world of managing the algorithms that make drugs?
I think we are. It shifts the human's value from execution, from turning valves and checking gauges, to oversight, to strategy, to problem-solving when the AI gets confused.
The operator becomes a data manager.
It's a completely different skill set. It really is a brave new world for the entire industry.
It certainly is. Well, that is all for this deep dive into pharma digital transformation. Thanks for listening, and we'll catch you on the next one.